Alright students, welcome back. We're continuing now with part 3 of our lecture. And I just actually went and played the part that I just made before, and okay, there's a lot of forces here, and they're explained in great detail in your textbook and so on, and you're going to see on like the questions that we have been showing, and so on the level of the material that we're interested in and so on. I mean, clearly you could spend a whole course learning about these forces and so on and how they create motions in the atmosphere. In fact, there are such courses. They're like 500 level meteorology courses. So we're going to take these 5 forces and we're going to try to use them to understand how, by Newton's second law, force equals mass times acceleration, how does this result in an acceleration of the wind? What kind of winds can we expect? And as I alluded to before we started that round of questions at the end of part 2 of our lecture, candidly, human brains aren't great at that. Human brains are not good at thinking about 5 forces at the same time. Human brains are made to think about 2 things, like to compare 2 things or contrast 2 things at the same time, maybe 3. And so it's better if we can try to think of situations in which we can assume that maybe some of these forces are much weaker than others, and then we can just ignore them. It's better than if we can come up with, well, we have 5 forces, but could we think of situations where we wouldn't have to worry about friction? Could we think about situations in which we wouldn't have to worry about the Coriolis force? And then with just the 2, maybe 3 forces that are left, come up with some kind of force balance where, oh, I see, in the real atmosphere under these conditions, only these 2 forces are acting and they balance each other, so there is no acceleration. It makes sense. That's the aim here. And because it's kind of the coolest thing to think about in a meteorology class, let's talk about tornadoes. Alright, now when we get all the way, I can't remember if it's Module 6 or Module 7 of the course, but we will hit a time in this course where we're talking about tornadoes in more detail. But for right now, it's enough to know just from your own experience of like watching TV shows and stuff. I hope you don't have your own experience of a tornado itself. Air is spinning around a tornado. It's spinning horizontally around an axis of the tornado, and it has very strong winds. Clearly something accelerated the winds to a very strong speed, but once the winds are in the tornado, we're going to kind of assume they're not actually speeding up or slowing down. There's no acceleration happening. What forces are then at work if we can make those kinds of assumptions? Well, it's going to turn out that the pressure gradient force is going to be very important in tornadoes. We don't have good measurements of what the central pressure of a tornado is, but it's probably something like 700 millibars, which is a lot lower than the pressure around us. Therefore, there must be a very strong pressure gradient force pushing from the air around the tornado towards the center of the tornado. Gravity? Gravity doesn't really matter on horizontal motions. The Coriolis force? Well, it turns out not really. Remember, the Coriolis force works best on motions that are very fast and are very long-lived. Well, the fast I'm happy with on tornadoes, but long-lived. I mean, the truth of the matter is tornadoes just don't last that long. The force of the Coriolis force is not particularly strong at any given moment, and it just doesn't last long enough to add up to enough to actually be important. So, I'm going to say the Coriolis force is probably weak enough we can ignore it. Centrifugal force. We abbreviate it CN for historical reasons. The centrifugal force sounds like it would definitely have to be important in a tornado. Clearly, the air and the debris that is going around the center of the tornado is experiencing a very strong rotation and therefore a very strong centrifugal force. Friction. Okay, now that friction's a hard one to think about in the context of a tornado. Let's go ahead and say we're going to ignore it. Okay, when I get to the tornado lectures in Module 6 or Module 7, wherever they are, we might bring friction back into it, but for now, let's just say, even if there is friction in a tornado, it isn't the main thing going on. It isn't like air from the tornado rubbing against the ground is slowing the tornado down all that much, okay? So, if we take a chance and look at these tornado motions here, we basically have narrowed it down to 2 motions. Now, on these arrows over here, what I'm trying to illustrate with the big fat arrow is that's like the rotation around the center of the tornado. We're looking at the tornado from above. And I can see that we must have only 2 forces at work. And we're going to buy that this idea that they're in balance. That the tornado isn't accelerating and getting faster and faster and faster, and it isn't weakening. We're talking about at a period of time in the tornado when it is holding its strength, it's maintaining itself. Well, the blue arrows on there are illustrating the direction that the pressure gradient force is acting at any given location, pushing air from the relatively higher pressure outside of the tornado towards the very low pressure at the center of the tornado. every air parcel that is going around the tornado is experiencing a centrifugal force, which I have illustrated there with red arrows, pushing it away from the center of the tornado. As it rotates, frankly, quite quickly around the center of the tornado, it is experiencing a strong centrifugal force pushing out. And in fact, this is the force balance that explains tornadoes, and in fact explains other rotational motions too, in certain kinds of phenomena like dust devils and so on, but we'll get to those at a different point in the course. Or maybe we'll mention them on a later slide, I can't remember. But this notion that under certain kinds of conditions, particularly in tornadoes and dust devils, a few other things, in those particular conditions we have a balance between only two of the forces are really big, in this case the pressure gradient force and the centrifugal force, and they're balanced. The pressure gradient force is pushing in, the centrifugal force is pushing out, and the air parcel just continues to, it does not accelerate, it just continues to orbit around the outside of the tornado. This phenomenon has a name. We call it cyclostrophic balance. See that word there at the bottom of the slide? Cyclostrophic balance. Or tornadoes and dust devils and water spouts and things like that have cyclostrophic winds. Cyclo is a Greek word part that means something like turning, or it actually has to do with snakes. It's a complicated word part. And trophic has to do with how it turns. And so it's a word that tells us that it's about how certain kinds of features are turning. Tornadoes, dust devils, water spouts, things like that. Okay? See how this idea of just narrowing it down to like two forces that are going to be our most important part, and then hoping we can find situations where those two forces are equal but opposite, led to a powerful understanding. Here we are only in the second module of this course, and you actually understand how the winds are going around a tornado. Neat, okay? We don't yet have the whole meteorology of why tornadoes happen and all that kind of stuff, but we at least understand that. Alright. I can't emphasize enough, though, how this cyclostrophic balance is an example of a force balance. It's an idea, a model, a conceptual model that we have that explains how, that approximates, is even a better word, how the real winds are acting around a tornado. I mean, in the real tornado, there are other forces at work. There is a small role for the Coriolis force. There may even be a small role for things like gravity and so on. But this is a pretty good approximation to what the real forces at work in a tornado are. In fact, it's a big part of how we know what the central pressure inside a tornado is, how low it is and so on, because we can actually figure out what kind of pressure gradient force we need in how big it needs to be in order to balance the observed centrifugal force. This is a pretty powerful tool. It approximates what the real wind inside the tornado is doing. That's a powerful tool. Let's apply a powerful tool like this to another set of other phenomena, cyclones and anticyclones. Cyclones and anticyclones. Oh yeah, no, actually, we gotta make sure we know what those are, right? Cyclones, we often use the word cyclone interchangeably for like tornado or something like that, but that's absolutely not right in a meteorological sense. Cyclones are big, broad areas of low pressure on a weather map. They're usually labeled with the letter L. They move over the course of days. There's one kind of centered here over Colorado on this map here, but I mean the area of low pressure spans several states. It's a big phenomenon. That's called a cyclone. Anticyclones are broad areas of high pressure. They also are moving, the right word actually in meteorology is we say they're migratory. And they are generally marked with H's on a weather map. So like on this particular map, there's a big area of high pressure centered on, it looks like West Virginia. But the area of high pressure spans, you know, from like Illinois up to Maine or something. They cover quite a few states. These are big phenomena. They're not like a tornado where it's only at most like a mile wide or something like that. Cyclones and anticyclones are a big part of the day-to-day meteorology in our part of the world. Why one day is warm, one day is cold, or something like that. Now, we're going to have a whole course where we're going to be figuring out what these mean. But for now, let's start figuring out what the winds around them are doing. Well, what are the winds around a cyclone or anticyclone doing? Well, for the most part, we can approximate the winds as being horizontal. Okay, there is some vertical motion going on in a cyclone or an anticyclone. It's going to turn out to be important for other things too, but to a good approximation for now, let's say the winds are horizontal. So we're going to get rid of gravity as one of our forces. And they're going to be long-lasting. The winds are going to go around this cyclone or around this anticyclone. It's going to take days and days for that to happen. Well, when things are long-lasting like that, they're in motion and the motions continue for a long time. Sounds like the Coriolis force is going to be important. Okay. These cyclones, we normally label them on a map as to like where they are at the surface, but there could be cyclones at any different level of the atmosphere. So there'll be situations where we're talking about cyclones at the surface, where we do have to worry about friction, and there'll be situations where there are cyclones above the surface of the Earth, where maybe we don't have to worry about friction so much. Well, let's take a look at our list of 5 forces and figure out what we can and can't throw out. Alright, pressure gradient force. I think that's got to be in there if we're going to understand cyclones or anticyclones, since, the whole point of cyclone and anticyclone was they were areas of different pressure. There is a pressure gradient. Sounds good. We got to hold on to that. But we do get to get rid of gravity as being relevant to what these motions are doing, because we can say these are horizontal motions and they're not accelerating downward because of gravity or something like that. Coriolis force? Yeah, Coriolis force better be important for cyclones or anticyclones, because even though the winds aren't going to necessarily be as fast as like a tornado or something, and remember, speed is part of the story as to how strong the Coriolis force is. Another part of the story is just how long the motion lasts. Well, cyclones and anticyclones last for days. Later, I think it's Module 5, we're going to see all about the life cycle of cyclones. But for now, days at least, of how long they're going to last. Centrifugal force. This is going to be a hard one to decide. For now, we're going to say we're going to ignore it. But Dr. Shoggy, didn't you just sort of hint that cyclones and anticyclones rotate? Yeah, they do. So shouldn't we be taking the centrifugal force into consideration, since the wind will be rotating around the area of low pressure or rotating around the area of high pressure? Yeah. But here's the deal. Think of these cyclones. They are the size of many states. Picture yourself on a merry-go-round that's as big as the whole Midwest. Okay? And now it's rotating, but it's rotating so slowly that it's going to take days and days and days for you to go all the way around the outside. Whee! Are you really going so fast that you're going to, the centrifugal force is so strong you're going to go flying off the edge of the merry-go-round? No, if you're on a merry-go-round that's turning slowly enough that you're not being, that it takes a day or days to go around the outside, you're not exactly getting a huge centrifugal force. So we're going to throw centrifugal force out for right now. Well, what about friction? Friction is definitely going to matter if we're talking about cyclones and anticyclones at the surface of the Earth. But what about cyclones and anticyclones away from the surface of the Earth, elsewhere in the troposphere? How about this? Let's do it both ways. Let's start by talking about cyclones or anticyclones away from the surface so that we can throw friction out and only have pressure gradient force and centrifugal force to work with, and then come back and think about what if it was at the surface. Okay, so what we're going to do is we're going to start a block of slides here. They're all going to be labeled here, example, cyclones and anticyclones aloft. Look, I even made a glowing over here where it says aloft. Because this is going to be a very special situation. This is going to be winds that there's 5 forces acting on, but 3 of the forces are really, really small. Friction, gravity, and centrifugal force. We're only going to need to worry about pressure gradient force and Coriolis force. This is going to turn out to be a really powerful tool that we're going to be using quite a bit throughout the course of the semester. So it's obviously important. And it has a name. It's another force balance, because we're going to find out that the pressure gradient force is going to be equal and opposite to the Coriolis force. It's another balance. This balance is called geostrophic balance. Geostrophic balance. Geos, Earth. Trophic is turning. It is a force balance that exists because the Earth is turning. In other words, because they have a centrifugal force. I'm sorry, a Coriolis force. Alright, let's kind of start picking this idea up. Because, once again, this is a type of force balance. We are using this as a way of approximating what the real winds are doing. I mean, the real wind going around a cyclone or an anticyclone aloft has 5 forces acting on it. Gravity is acting on it. Centrifugal force is acting on it. Friction is acting on it. But they're a lot smaller than pressure gradient force and Coriolis force. But we're going to see that this is a good approximation to what real winds are doing. Alright. We're going to start making a map here. Just for the sake of helping you remember that there's a map. I've put a map in the background, okay? And what I did is I made a big area of low pressure off to the west and a big area of high pressure off to the right. And I've got some little lines on there. They're contours. Contours of pressure. I don't have them labeled, but clearly one of them, the one closest to the low, that would be some, relatively low pressure, maybe 996 millibars, and then 1,000 millibars, and then 1,004, and then 1,008 millibars, and then we're over here to where it's higher pressure. Okay, I didn't make full contours there just because PowerPoint is not the tool for the job to do such a thing. And that blue circle that I have drawn there in the middle, that's just supposed to be some air parcel. An air parcel would not be such a giant thing and so on. It's just, I drew it. Okay. There's an air parcel. It's just sitting there. What will the winds be doing? We clearly have some area of low pressure, or a cyclone, off to the west, and we have some area of high pressure, or an anticyclone, off to the east. What are the forces that are at work on this air parcel? Well, one is pretty straightforward to think about. It's the pressure gradient force, which I have labeled there with a red arrow. The pressure gradient force is going to be pointing from the area of high pressure towards the area of low pressure. It needs to be perpendicular to the contours around it, which I think I did a pretty good job drawing that. So it points towards the area of low pressure. Okay, so there's a force acting on the air parcel. If that were the only force acting on the air parcel would, by Newton's second law, accelerate towards the cyclone. But that doesn't happen, because there's a second force involved. The other force is going to be the the Coriolis force. Now, a leap of faith is required here, which then we go back and explain. We're going to say, at this point, because this is in geostrophic balance, we know that the Coriolis force and the pressure gradient force have to be equal but opposite. Okay? We'll come back then and figure out how that happened. Okay? But we're going to draw in green there a Coriolis force vector. It has to be equal and opposite to what we have in our pressure gradient force. Okay? If that were the case, then there'd be no net force acting on my air parcel. Therefore, it's no longer accelerating. Whatever it's doing, it's going to continue doing it. Okay, that doesn't mean it's not moving. It just means if it's going to be moving, it's not speeding up, it's not slowing down, or any kind of acceleration like that. Well, how would we get a Coriolis force like that? Well, remember, the Coriolis force has to be, in the northern hemisphere anyway, 90 degrees to the right of how the object is moving. In this case, the object being the air parcel. So in this case, if the Coriolis force is pointing off towards the right, well, off towards the east, let's say, that is opposite what we drew for the pressure gradient force, then for that to be 90 degrees to the right of the wind, that means the wind must be going straight to the north. The air parcel is moving straight to the north. So, in order for this wind to be geostrophic, in other words, for this air parcel to be in geostrophic balance, apparently it is not moving towards that area of low pressure, nor is it moving towards that area of high pressure. It's actually moving parallel to the contour lines, with lower pressure to its left and higher pressure to its right. That makes a pressure gradient force that is pushing one way, and a Coriolis force that's pushing the opposite way. They are equal and opposite, they're canceling each other out, and the air parcel will just keep doing what it's doing. There's no acceleration. It'll just keep blowing parallel to the isobars. This is the core thing of geostrophic winds, and it turns out, as long as we're talking about things happening above the ground where we can definitely not worry about friction, geostrophic wind turns out to be a really good approximation to what is going on. When we measure the winds using weather balloons and all that kind of stuff that we'll be learning more about later in the course, they are generally pretty good, pretty well match what we can calculate the wind would have to be to maintain geostrophic balance. We're not going to calculate the geostrophic wind in this class. Not that it's ridiculously hard, but we have other things to do. It's just a little math. Alright. In the northern hemisphere, geostrophic winds will always be parallel to contours with lower pressure to the left of the wind, higher pressure to the right of the wind. Cool. And there's a lot of things we can actually look at when we see the contours, and we can start figuring out what this approximation to the wind is really doing. For example, I took the map off of here, but again, these would still be on maps. But like, for example, let's say we have a weak gradient in our pressure. In other words, like for example, here are my contours, and they are relatively far apart. We would have a pressure gradient force going towards the area of low pressure. We have an equal but opposite Coriolis force. In order to get that Coriolis force, we have to have a wind that is pointing straight to the north, and it's 90 degrees, has Coriolis force 90 degrees to its right. But look what happens if we make the isobars closer together, if we have a strong gradient in the pressure. Well, remember what force is related to how close together the isobars are? The pressure gradient force. So the pressure gradient force, which I drew there as the red vector, is stronger. Therefore, we draw it as a longer vector. Coriolis force has to be equal but opposite to the pressure gradient force. So, how do we get that strong Coriolis force? Well, you get a strong Coriolis force by making the wind stronger. Remember, Coriolis force is proportional to the strength of the wind. The stronger the wind is, the stronger the Coriolis force is. So we have a stronger wind. So when the isobars were far apart, we have a weak wind. When the isobars are closer together, we have a stronger wind. Just by looking at a map of pressure where we can see how close together the isobars are, we now know something about the speed of the wind. Now, in a 500 level meteorology class, you would actually do the math and compute it, but we're just going to kind of be eyeballing it. Okay, where is the wind stronger? Where is the wind weaker? Now, let me tell you a way to remember this, okay? This is not how it works, but it's a good way to remember it. Think of the way the isobars are put together as kind of like hoses. When the hose on your is wide, the water can flow through it slowly, but when you have like a narrow tube and the water's got to get through there, squeeze through there, it shoots through there fast. That's how, like, when I was a student, I remembered it, okay? When the isobars are closer together, it's like the air's got to go fast to get between there. That actually has nothing to do with why it happens, but it's an easy way to remember which way it works. Okay, before we move on to part 4 of this lecture, where we're going to take this idea of geostrophic wind and start applying it to different situations, let's answer a couple quick questions about what we've just seen anyway. Question 8. Which of the forces are in balance when we say that the wind is in cyclostrophic balance? Keyword, cyclostrophic balance. Is it A, the pressure gradient force and the Coriolis force? Is it B, the Coriolis force and friction? Is it C, the pressure gradient force and friction? Or is it D, the pressure gradient force and centrifugal force? One of those is the right combination of forces that are equal and opposite to each other when air parcels are in cyclostrophic balance. Make a choice from the 4 options and get a little feedback before you answer another question.